Hello, welcome to my Computer Science 610 Assignment 4 presentation. What I'll talk to you today about is code smell severity from a developer's perspective. My name is Kirsty Balance. So what I'd like to cover in the next short 20 minutes is I'll talk to you about my research question. Then I'm going to follow that up with the code smell metaphor and then discuss disparate interpretations of that code smell. I will circle back and review my research question right before I talk to you about the method and then the procedure that I actually took. I'll discuss the evaluation of my results, briefly discuss some related research, and then finish that with some future work. So jumping right in, my research question, as shown on the screen, is to inaugurate a precise relationship between code smells and their effect on developers' teams' productivity and morale to understand the most important code smells. That seems like a whole bunch of words right now, so I'm just going to go through a couple more slides and then I'll circle back to the research question. So what is a code smell? I know it's a funny term, but basically it's a metaphor that was coined by Kent Black in 1999 when he was building a book to highlight code refactoring and maintenance best practices. And what it means is it's a surface indication that can potentially correspond to a deeper problem in the system. So I liken it to natural gas, actually. So here in BC, we have BC Hydro that injects their natural gas with the smell of rotten eggs. And what the purpose of that is if you were to smell rotten eggs in your home, it's an indication that there's a gas leak. So the smell indicates danger. Here, it's the same thing. So the code smell itself isn't exactly the problem. It just can indicate a bigger problem. So if you think of the list here, the first one is duplicated code. So that's not technically a problem, but when you have duplicated code throughout your system, the potential to, if that block of code needs to be updated or maintained, the potential to miss some of its duplications is greater. So why not move that into a single class and use that and then you only have to change it in one spot. Anyways, the code smells are here. If you want to read through the list, feel free to hit pause and read more closely. But I'm going to move to the next slide. So since the code smell metaphor's inception in 1999, there's been a ton of research attributed to this realm. Specifically, lots of automatic code smell detecting tools have been created. What's interesting, though, is that of these automated detection tools, there was a survey done by Razul and his team to see the effectiveness of these tools. And what they discovered was that there's actually very disparate interpretations of the code smells across not only the detection tools, but lots of researchers. The detection tools just happen to bring it to light. So what I mean by that is, like, if we were to look at the three, Razul looked at three automatic code smell detecting tools called Checkstyle, PMD, and JDeodorant. And what he did is he ran those against the same code base, the Gantt project, and discovered that with the three code smells he looked at, there was extremely varying results. If we look at the long method results, we can see that Checkstyle discovered that there was 14 instances of long method present in the Gantt project, whereas PMD says there's 18 instances, and JDeodorant says there's 195 instances of long method in the code base. So those are extremely different results for the same code smell on the same code base. So that indicated that there is these disparate interpretations of how to measure these code smells, and it goes back to the definition. So the reason for these differences ended up being that I don't remember which one's which, but one of them looked at lines of code count, whereas another one looked at number of characters count, and another one included comments, whereas the other ones excluded comments from the overall count. So it all goes back to the fact that the definitions themselves are a little ambiguous and open to interpretation. So there is a need for further research in the code smell community to generate a universal and standard definition. So in order to do that, I argue that it should not be a holistic approach. So do not try to solve all of the code smells all at once. I think it should be iterative, focusing on the most important code smells to the least important code smells. Now, I've got them highlighted there. That's just an example of how it could be. That's not actually the most important to least important. It was just to demonstrate that it should be segmented into blocks of code smells for further research. This moves away from a breadth approach to more of a depth approach, and allows researchers to focus more closely on the code smells, the inherent nuances of the code smells themselves. So, circling back to the research question, to inaugurate a precise relationship between code smells and their effect on the development team's productivity and morale, to understand the most important code smells. So basically that's saying, let's find the most important code smells to research first. And to do that, let's let the developers decide, since they're the experts and they're the ones that have to deal with these code smells. So this is my theoretical method. It's got 5 components. The first is code smell identification. So there is already research out there to try to identify the most important code smells to developers. So I just wanted to review a few of them and generate a cohesive list of those code smells. From there, depending on what code smells were identified, I would collect sample code fragments for each of the code smells, between, I don't know, maybe up to 10 code samples each. I would compile those code samples into a document and provide that to a group of developers, where they could rank the code smell from most severe to least severe, and provide a couple sentences why. I would collect and analyze those results. So that was the theoretical method, and what I actually did was I reviewed 4 studies that focused on code smell importance to developers, and came up with a list of 4 code smells. That was long method, God class, feature envy, and refused bequest. But what I also discovered is that of these classes, these code smells, developers only considered them to be a problem, to be the most important, depending on severity. So that ended up highlighting the need for a severity measure. So when I collected code samples, I made sure that I collected varying degrees of code severity, some that were more severe than others, or at least in my opinion. And I ended up compiling those into a single PDF document. So I grabbed 3 to 7 code samples for each of the code smells, and put them in a PDF document. The reason I use PDF is because I really wanted the format to be maintained. When reading code, it's really hard to read it if it's just black and white. So I wanted to keep the color coding, keep the line numbers in there, but I also provided a description of what each code fragment was doing. And this, in addition to that, wherever possible, I also supplied the fixed code or the refactored code with the code smell removed. This was so that I could have the developers focus on not so much on what the code was doing, but how it was doing it. So like I said, I compiled that up into a single PDF document and delivered it to the developers. I sent it to 10 developers. 4 responded with their rankings, and of those 4, 2 responded with text responses. So it was a little disappointing that only 2 provided the text responses, but I was able to work with that data anyways. From there, I collected the results. So the way I collected the results is I stored each of their most severe code samples into a cell. So in this table, you can see that the developer 1, 3, and 4 each selected code sample 2 as the most severe from the code samples provided for the God class. I did the same with the text feedback, but instead of putting their ranking, I put their actual paragraph that they provided. From there, I analyzed the results. I'll talk about that more in the evaluation portion of this presentation, but from a high level, I just measured their agreement with the rankings, and I also ended up doing something a little bit unexpected. It wasn't sought out in my method, but I was hoping from the text responses that I would be able to find a pattern in the text, like they would sort of give the same reason, but that wasn't the case. So what I did is I looked to some other research studies to see how they used the text feedback they got, and ended up remapping it to sort of underlying categories that were present in their text responses. Again, I'll talk about this more in the next slide, which is the evaluation. So for my rankings, what I discovered was there was quite a bit of agreement on which code was the most severe. So walking through each, the God class, the developer 1, 3, and 4 all chose sample number 2 as the most severe. Developer number 2, I was just actually abstained from answering this one altogether. So he said that the reason he did not want to pick one for the God class is because he doesn't understand how it could be a problem, how a God class could be a problem. So I'm hesitant to put it to 100% unanimous because he did abstain, so I left it at 75, but it just sort of highlights the fact that a developer's inexperience with a code smell can play a factor into the results. So for feature envy, it was unanimous across the board. Each of the developers chose code sample number 3 as the most severe. For refuse bequest, it was a 50-50, so it was a little bit of a mixed bag there. And for long method, again, it was unanimous. Now, for this code smell, I'm hesitant to say that it was completely accurate, I guess, because code sample 4 happened to be the longest code sample among the bunch. And I personally didn't think it was the most severe. So I have a feeling that the fact that it was called, the code smell is called long method, they ended up just choosing the longest one. I'm not sure, but that's just my theory there. So if I was to redo this research, I think I would change that word from long method to one of its other names, which I think would yield better results. For the text-based responses, as I mentioned, the text responses were not, there wasn't a lot of overlap in purely the words. So using a classification method that I'll talk about in the next slide, it ended up remapping the text feedback to these categories. So there ended up being sort of 4 predominant categories that were revealed when these were classified, which I thought was super interesting. So severity ended up being a combination of maintainability, module dependence, task relevance, and readability, which makes sense to me. The full list of potential categories can be seen in this related research. So Say Lim and his team ended up doing a study called How Do Developers Select and Prioritize Code Smells? And what they did is they actually reached out to developers and provided full code bases that had code smells pointed out, and asked them to provide text-based feedback. So once they got their text-based feedback, the team used these 12 categories to classify the responses. So it's something missing from my research is the fact that modular importance could never be measured in the code fragments that I provided, because I only provided, like I said, the fragments instead of the whole body of code. So you couldn't determine modular importance if you can't see the whole code base. So if I was to redo this research, I would provide full code bases and just simply point out where the code smells were. But anyways, that was their results from their research, which I thought was kind of interesting. Another very interesting related research is an approach to prioritize code smells for refactoring by Vidal and her team. So what they did is they moved away from just simply asking developers to rank it, and instead added 2 additional criteria. Okay, so the first criteria is stability of related components. So what this means is that where a code smell occurred, they would look to see the version history to see if it's changed often. The theory being that if it was very infrequently changed, the severity is a little bit less, because it doesn't change very much. So does it really matter if it's got some smelly code in there? Whereas if it was changed frequently and it had smelly code, then maybe that becomes a higher priority. Their second criteria is this idea of surveying developers. So it's similar to the research done in my research, where they did like the Likert scale. They measured severity on a 1 to 5 scale, 1 being not very severe and 5 being very severe. And then the third criteria they used is called related modifiability scenarios. But this just means is does the code play a pivotal part in the system, or is it just a minor, infrequently used portion of the code? Theory being that if it was very central and controlled a lot, then it would be more important than something that just gets called once in a while. So in conclusion, from my research, I did discover that ranking severity in a Likert scale did show obvious patterns. And what this indicates is because they showed patterns, there could be potential to automating the severity measure. Text-based responses initially did not have any overlap, but when it was recategorized, it did show some patterns. Again, this indicates that if patterns can be extracted, then perhaps severity could be automated. And lastly, developer inexperience did have some impact on my responses. So actually, all the developers that I surveyed said that they'd never heard of the concept of code smells. So if I was to ever redo this research, I would try harder to get responses from a mixed bag. So I would like to have people who have not heard of it and people who have heard of code smells. So I guess that brings me to some future work. I really was interested in the 3 component criteria used by Vidal. I would like to combine that with the criteria used in the Say Lim study, using text-based feedback and remapping it to categories. And I would like to investigate some machine learning potential. So is there a way that machine learning could be used to determine the severity, predict the severity of some code smells? So that brings me to the end. I'd like to thank you for 20 minutes on your Easter weekend.